Hi everyone, it's a pleasure today to have with us Dr. Ishai Menashe from Microsoft Research today. Ishai received his PhD from Technion in Israel and then postdoc at MIT, after which he has been working at Microsoft. His areas of interest are quite varied: optimization, game theory, and in particular right now on distributed resource allocation for data center. So please welcome Dr. Ishai Menashe.
Thank you guys. It's a great honor to be virtually with you, and I hope to visit you physically soon. Okay, so as Srinivas mentioned, I've been sort of focusing for the last 2 or 3 years on the sort of it's a buzzword of cloud computing, but essentially there is a lot of work behind it, and specifically what I'm sort of focusing on is more on the optimization and resource allocation aspect in large data centers. So today I'm going to give you a glimpse of the things that I'm doing, and I'm going to present 2 separate pieces of work which have been sort of not remain only on paper, but also have been applied to some extent in Microsoft data centers. So just as a brief background on myself is that I come from sort of a more theoretical background. I would say very similar to Srinivas and other folks there, and but coming here to the real world, so to speak, is I mean there are many differences in the way that you do things, and when you come up, let's say, with a resource allocation mechanism, it's not necessarily, let's say, the most beautiful one or with rigorous proofs, but what's more important is that it can actually work in practice, and that if it's being implemented, then it's not too complicated, and it takes into account simplicity and other factors. I mean that you don't see when you're writing things on paper, but you see when you actually confront the real system. Okay, so I have one slide of motivation. Just I want to get right to the point. So the context is the modern data centers, and so a word that appears in this bullet is multiple. So we have so it's a large data centers. We are talking today about tens of thousands of machines and even beyond. Multiple resource types that need to be divided between applications, users. Resources are CPU, bandwidth, storage, and so forth. Usually when we come, and I'll give you some concrete examples today, when we want to optimize something, it's not like a simple optimization criterion. It's always, there are multiple considerations, and usually there's interesting trade-off. You want to optimize something and you're actually hurting a different metric that is also important. Heterogeneous customers, some are big, some are small, some care about latency, some care about bandwidth, some care about other stuff. And of course, in the context of cloud computing, which I won't be focusing much today, just very briefly, I think towards the end, a multi-tenancy that we see like in of course, EC2 or Azure. We have multiple users that are sharing the same physical resources, and that creates all sort of interesting problems. How do you give each one of the users the feeling that he's he gets like performance isolation, and he can get the quality of service independently of what others are currently doing. So this brings into the picture a lot of challenging resource allocation and control problems, and I think that one of the biggest challenges that is modeling correctly what you want to solve. It may sound very obvious, but sometimes you hear about certain problems that you talk to production groups, and there are certainly smart people, and they are worried about certain aspects, and they can clearly state what bothers them. But to bring it to sort of to the level in which you can apply rigorous solutions, it takes some kind of you need some kind of modeling skills. You need to abstract the problem properly and solve it, and then maybe return to the actual physical system and relax some of the sort of simplifying assumptions. So what I like to do in particular is come up with algorithms that are backed up by some kind of, I would say, inspired by theory. So that there is some, some hope, or if we can get guarantees, fine. If not, then there is some principle that is sort of derived from either optimization or other fields. And another important aspect, which, as I mentioned, I haven't done much before joining Microsoft. You need to evaluate what you're doing through at least a prototype, and as some kind of a prototype that uses real traces or real data. And when you say that, when you need to prove that something is working, is not just proving a theorem or a lemma, it's actually showing benefits on a prototype. So that's all what I have in terms of like general background, and I'll be discussing two works that have appeared in CCOM 212 and 213. And the first one is titled Surviving Failures in Bandwidth-Constrained Data Centers. So the story is as follows. We have, let's say, in large applications such as Bing, there's actually internal functions or internal services that need a certain number of machines. Okay, so let's assume that all machines are doing the same for that particular service. There could be a big service that needs hundreds of machines, could be a small service that needs very few machines. And the question that we are dealing here with is how to place the services in the data center. Or in other words, a certain service requires, let's say, 100 machines. Which physical machines do I allocate to that service? So it's a mapping from logical machines to physical machines, if you wish. So there are a few criteria here that kick in that are very important. The first is fault tolerance. Okay, so services should survive infrastructure failures, such as the switch going down. So for example, if Srinivas has a service that requires 100 machines, and we put we allocate all the machines in a container, in the same container, and let's say that the switch on top of this container goes down, then all these machines are sort of lost. So we certainly want to avoid these kind of situations. So there is over provision that should partially consider or be some kind of a remedy for fault tolerance, but it's not enough. So you cannot over provision the data center. Cost is a major factor, and you just need to optimize for fault tolerance. And I'll give more precise definitions later on and some cartoons which will make the context much clearer. The second metric of interest is bandwidth. So we certainly want to reduce the bandwidth on the congested links, and in particular, mostly we refer to the core of the network. And while we place certain services, we want to make sure that we don't overload the core capacity of the data center. And again, the same argument that in principle you could double the bandwidth of the data center, but you don't want to do it. Again, these are cost considerations. So you want to operate. So you cannot just solve the problem by just buying more stuff. So a third criterion is that whatever you do, you cannot go wild with a fancy algorithm that will sort of just create churn in the data center. You'll be moving machines from one place to the other like crazy. This is out of consideration. Whatever you do needs to be efficient in terms of the churn in the data center. And this will become clear once I'll give a few examples. So when we are, in particular, when in the context of machine moves, so a move, for example, is, let's say we have some kind of, we placed Srinivas' machine in one rack and we want to move it to another rack, then it's in terms of what goes in the background, it's a lot of hassle, right? Because we need to transfer the context of his machine, copy a lot of data, and so forth. So these are the three criteria that sort of will drive our approach. By the way, if there are any questions at any point, feel free to stop me. I see that we have like, the crowd is not that large, so it can make it more interactive for sure.
What do you define as the definition, sorry.
Yeah.
What do you define as the definition of a move? Are you
Yeah, I will define it more precisely later. Okay? So the Bing context, which actually started working on this with the Bing folks. So for those of you who don't know, Bing is the search engine becomes more and more popular actually, and so if you think of Bing, so Bing has its own data centers, and services of Bing include the web answer, actually getting the answer, but not only that, of course, the supplementing ads, social search, data processing. These are all services, and actually there are thousands of services in an application, in a big application such as Bing. So each service, as I mentioned, requires a different number of machines, and so here's a cartoon that hopefully will make things a bit more clear. So that's the cartoon of our data center. Let me move the picture here. Yeah, okay. So as I mentioned, the two main criteria are fault tolerance and bandwidth. So here you see the data center, and let's assume that we have only a single service that requires 8 machines, okay? And the racks are of 4 machines, okay? So the allocation on the left is of course is bad in terms of fault tolerance. Why is that? Because there is the AG switch here. If the AG switch goes down, then the owner of this service loses the 8 machines. Okay, so the fault tolerance is low. In other words, the worst case survival, if we take into account, so that's a metric that we're going to use, which is namely how many machines survive in the worst case. Here in the worst case, none of the machines survive, so the worst case survival is 0. But what's good about this solution, that is the communication. Let's assume that the different machines talk to each other. The communication here is pretty, it remains local. It doesn't go through the core of the network. So that's a good solution in terms of bandwidth. On the other hand, as you already may figure out, the solution that spreads the machines across different racks is good in terms of fault tolerance, because no matter which AG switch goes down, half of the machines remain, and assuming a single failure, of course, so half of the machines remain, so the worst case survival rate is 0.5, but the drawback here is the bandwidth consumption. Again, assuming that all the machines talk to each other, the communication obviously goes through the core of the network. So as you can see, there's actually a pretty strict trade-off between fault tolerance and bandwidth. Yes?
Question. So it's not clear to me why the bandwidth would be higher. I can see that you would imagine it's the same total load, right? So,
right.
So if you're talking about bandwidth in terms of sort of bandwidth times distance, then I'll buy it. But in terms of total packets, it should be about the same.
Right. I'm not saying so. If I wasn't clear, let me clarify that. So I'm not saying that in one configuration the bandwidth consumption is higher than the bandwidth consumption is exactly the same. The question is where do this transmission takes place? And in this solution, it doesn't go through the core. So assuming that I only care about, and the assumption is that we are making is that we care only about these links, the core links, because these are usually the most expensive ones and congested ones, which you want to keep sort of utilization at plausible levels. Then, of course, the right configuration goes through the core, goes through these 2 links, and the left configuration doesn't.
Okay, I understand.
Yeah. Okay. Great.
So one other follow-up question.
Yeah.
Is they're not looking at power consumption in this at all, right? The comparative power consumption.
Sorry. Can you start?
Are you considering power consumption of the left configuration versus the right configuration?
In what sense?
Like rack power consumption.
No, we are not considering that here.
Is that an issue, or is that, I mean, is that a real issue?
As far as I know, it's not a big issue, and it won't change much from one configuration to the other. You know, the assumption here is that I'm showing only a single service here, so you could say, oh, but in this configuration, another advantage is that you are keeping these two racks empty. But let's assume that, just for illustration, let's assume that the racks are occupied by some other services, okay? So it's not a real issue. I mean, I only showed one service just to make life simpler, but you should think of multiple services, and then it's not about turning off racks, and I'm aware of works around this area, but it's not the context here. Does it answer your question?
Sort of. Yeah.
Sort of.
I mean, I say sort of because I think a relative understanding of the power consumption of the core versus switches versus rack is actually perhaps quite important as something to optimize, along with all this, along with fault tolerance and whatever.
I see. I see. So, you know, just to say it in different words, I think that the assumption here is that the data center as a whole is shared by many services, and utilization is quite high, and there is nothing much that you can do in terms of power awareness that you can save by turning off certain equipment and so forth. It's something that could be done, could be perhaps be another consideration, but not under the settings that we are operating at.
Fair enough. Okay.
But I'm saying it's a valid point. I mean, I'm not saying that it's not a valid point. I'm just saying that in our context, it's not very relevant. But okay. I'll be happy to take it offline if you have more specific sort of observations, and I'll be happy to discuss it further with you.
I don't have a specific knowledge of the relative power consumption of those three layers. I was just wondering if you did, that's all.
Okay. Yeah, I do have some knowledge about it, but again, the context here is a bit different. Yeah. Yes?
For the service here, so does each service require all the 8 servers to work, or part of it?
Okay, so the assumption is that, you know, it wants all the machines. That's the best case. If you think of, for example, some kind of a web server, and you want to basically, the more machines you have, the higher the sort of the rate or the incoming request rate that you can support, right? So there's sort of an implicit assumption here that you want the most of your allocation, but because it's a distributed application or service, it should be designed in a way that it's not a total catastrophe if half of the machines go down. The service can still operate, maybe at a lower throughput, maybe under like suboptimal operation, but can still function.
Okay, it's like more like scalable thing. It's not a binary.
I would say the more machines that are alive, the better.
Okay, got it.
And by being aware of fault tolerance, you actually want to improve this. The metric that we are using, again, you could think of different metrics or different specific criterion in fault tolerance, but we are using the worst case survival rate.
Okay, got it. Okay.
Okay, guys. So thanks for the great questions. So just a bit about the algorithmic context. So actually, you know, it's quite if you want to optimize for both, and I'll be more formal later on, but if you want to optimize for both fault tolerance and bandwidth, so actually each problem separately is NP hard and actually belongs to those problems that are hard to approximate. So in particular, the bandwidth, if you look at bandwidth in isolation, you want to minimize the bandwidth consumption in the core, Then the algorithmic context is that of sparse cuts and spreading metrics. There has been a lot of work, but it's sort of a very hard problem, and especially when the pieces that you want to sort of separate between or put together are not of equal size, which is our case. The fault tolerance reduces, under simplifying assumptions actually, reduces to the maximum independent set problem. Again, one of the hardest problems out there to approximate. So, and moreover, we want to obtain a solution that takes into account, is not sort of isolated from what's going on in the data center now. The assumption is that you are starting from a given configuration, and you need to move to a better configuration in terms of both bandwidth and fault tolerance, but you want to do it with a small number of moves. And actually, all these classical problems don't take into account the number of moves. Okay, so a bit of insights that we obtained by looking at data. So here you see the communication pattern in the data center, and actually, you know, we put in the X. This is the matrix. We put the services on the X and the Y, and the color is orange or green or whatever if there is a communication between a pair of services. Okay, so what's nice about this this measurement is that we can see that the communication pattern is very sparse. We see a lot of white areas, and it's very skewed. Okay, we can see services that are very talkative, if you wish. Okay, for example, these services here talk to all the services, or most of the services, while others talk in very small and basically in just to very small number of services. So this actually gives us hope because, you know, the guys that are white, basically, you can sort of improve their fault tolerance almost without worrying about bandwidth at all, right? Because there is no bandwidth consumption between, they don't talk to anyone. So this was something nice that we started with, and we said, okay, there is some hope in this problem that we can sort of obtain a nice solution simply by moving the guys that don't talk, improving their fault tolerance, and keeping local the guys that are very talkative. So basically, yeah, this is one of the main observations. The other observation that we obtain while we analyze data is that the actual what we call fault domains are not aligned to each other. So, for example, this is a cartoon of the data center. Okay, so you could have a situation in which you see that container A is actually uses power from both power source 0 and power source 1, and also container B uses the same power resources. Okay, so the basic units are not the containers themselves when we come to reason about fault tolerance, but actually the combination of power 0 and container B could be viewed as a single what we call cell. Okay, if either power 0 or container B fail, then these machines here go down. The fact that we don't have an exact alignment of the fault domains complicates the optimization problem.
So this actually gets to a question I have, and maybe you'll just tell me that this is the answer. Is it correct to assume then that it is just the power itself, what the particular power source is the primary failure mechanism you're concerned with? Or
sorry,
are there
I didn't hear the second part.
Sorry, my voice is kind of bad. Is it just the power source itself is the main failure mechanism you're concerned about? Or is it actually, you know, what is contained, or is there some other cabinet failure that you need to worry about as well, or are there other types of failure modes?
So here is the power source itself, but there could be a network of power sources that could fail at the same time. That's correct. So there are different hierarchies in terms of the power mapping. And here I'm just using the power source itself for illustration, but you're right in your observation. It's more complicated than I just showed here. Okay, so a bit more formality, and I won't be, so all the mathematical guys will excuse me, I won't be 100% formal in this talk. I'll try to be sort of 70 or 80% formal, and because I just want to, I think it's more important to sort of get the main ideas and not fall into the math and formalities. So, but I'll try to make it as comprehensive as possible. So here's the model the problem in a nutshell. So we are giving the topology of the data center, including the fault domains mapping. We know the number of machines that are required for each service, and we have the communication matrix which we measured, and we know how much each service talks to another service. The metrics that we care about are the fault tolerance, and again, as I mentioned, in particular, we are looking at the average worst-case survival rate. The worst-case survival rate is a percentage of servers that remain under the worst-case single failure. Bandwidth is the total bandwidth consumption in the core, and NM, number of moves, is number of servers that need to be re-imaged to get from an initial or a given allocation to the proposed allocation. So one way to state the optimization, and in an informal way, because I'm not introducing the optimization variables, we want to maximize a linear combination of the fault tolerance and the bandwidth. Alpha is sort of some kind of trade-off coefficient, subject to number of moves need not exceed a given constant N0. Is this clear, more or less?
Yes.
Okay. I'll get a bit more formal in the subsequent slide. Here it is. So the way that we approach this problem, we said, okay, there are these approximation algorithms, but we have these multiple metrics. We want to have something nice that can actually be simple, that can be deployed in production. And what we did is the following. We defined a quadratic cost function, which is basically sum of squares, where each element in the sum of squares denoted ZDI is the number of machines of service I that are affected by the fault of domain D. Okay, so, and actually the basic decision variables are the allocation within each cell. So this is here the XCI. I don't think we need to go into this. It's enough to just think about the ZDIs. They are not the basic optimization variables, but they are related via an affine transformation to the basic decision variables. So what is this ZDI and what's the reasoning here? So let's look at two configurations. So this is again our data center with power sources and containers. And in the first configuration, the upper configuration, all the machines, the 8 machines, are allocated to this cell here. Okay, so the sum of squares here is large, okay? Because why is it basically 64 plus 64, right? Because if container A, if the switch of container A fails, then we are losing 8 machines. Okay, we have 8 machines here, a mass of 8 squared, and if power 1 again goes down, then again the effect is on 8 machines, 8 squared. So 2 times 8 squared, 128. On the other hand, the configuration in which we spread things around, of course, gives us a value of that cost function of 64. So, you know, basically, yeah, we can do the math, but basically we have 16 times 4, okay? 4 squared times 4 for the four different types of domains that we have. So as you can see, there is an anti-correlation between this cost function and the fault tolerance metric. So the hope is that by minimizing this function, we can get very good fault tolerance, spreading of fault tolerance. Again, here in this slide, I'm only considering fault tolerance. I will add the bandwidth later on if I didn't mention that. So what's nice about this function? That sort of It's sum of squares. It has some nice properties, convexity. Although we are not dealing. I'm a bit cheating you here because we are dealing with discrete variables and not continuous ones. But again, it's a nice function. It's a potential function that behaves nicely. And the nice thing about it is that sort of if you think about gradient-like moves, and I'll explain what's a move in this context, then you gradually improve the cost by doing small moves. Okay, you can gradually improve the cost, reduce the cost, and actually increase the fault tolerance without having to remember what you did so far. So it's like a memory-less approach, which was very important to the product groups. They don't want an algorithm that you start calculating things, something goes down, and then go figure out where you were and what you want to do. So in this context, this is very simple and intuitive and nice to work with. So as I promised, and there was a question before, what is a move here? So the move is simply the simplest move that we can think of is what we call a swap. So here we have two services, the red service and the green service, and a swap is basically taking one machine that belongs to the red service and giving it to the green service and vice versa. Okay, let's see if the animation works. Okay, so you see this is a swap. This is actually a swap that improves the fault tolerance. So what we do, we have a global cost function that sort of represents the current state in terms of fault tolerance, and we improve it gradually by choosing the best swap. Okay, what is the best swap? The swap that will reduce by most this sum of squares function. Okay, so actually in practice we of course don't examine all the possible swaps. What we actually do, we just pick a large enough number of swaps, and we take the best one out of these swaps that are examined. And this is good enough if just the intuitions that, you know, if you recall from convex optimization, you don't necessarily need to move in the gradient descent direction, as long as you're sort of you have a negative derivative. You can move in what's the so-called ascent direction. Okay. So now, how do we deal with bandwidth? So, you know, one approach is sort of an approach which is very expensive in terms of machine moves, is sort of do some kind of a cut procedure on the entire graph, on the entire data center, on the communication graph, and sort of pick the pieces that talk less to each other and put them in the same physical entity. The problem with that is that basically a cut procedure that is sort of doesn't take into account the current. There's no way of incorporating the current state of the cluster. So if you want to go to this kind of solution, you basically need to take into account that you might be reshuffling all the machines, and this is totally unacceptable. So what we did was something very simple. We just added a penalty to the cost function, a penalty that takes into account the entire bandwidth consumption in the data center. So we are losing the convexity, and this can be defined formally with the decision variables. If you refer to the paper, you'll see it in a more formal way. We basically minimize the combination of the fault tolerance and the fault tolerance cost function, which we defined earlier, and the total bandwidth consumption. So we call it FT plus bandwidth. Okay, so actually maybe the best algorithm would have been to start with the cut, to start with the configuration that is good in terms of bandwidth, and then improve the fault tolerance by this kind of moves. But the algorithm that we eventually implement is the one that skips the first step here, the cut, and just does step 2, basically the gradient descent moves using machine swaps, which minimize the sort of the combined cost function of fault tolerance and bandwidth. Any questions? This? Okay. Okay, so here are some results, actually from one of the data centers. So the goal is to improve fault tolerance and bandwidth. This is the initial allocation. Is basically we are comparing relative to the initial allocation. If we optimize just for bandwidth, we'll end up somewhere here. We're actually going to hurt fault tolerance if we are, and this is based on the trade-off that I've shown you before. If we are optimizing just for fault tolerance, we'll end up hurting the bandwidth consumption. And so this is sort of the benchmark that I mentioned. Start with a cut and then do these gradient moves on the FT plus bandwidth cost function. But this moves all the servers, and here you can see the improvement. So here we have some kind of the so-called Pareto curve, which corresponds to different values of this alpha. Okay, different trade-offs between fault tolerance and bandwidth. So this is what we get. And now this is the actual algorithm that is more practical for production. And this is when I'm going to show different curves that correspond to different allowed of, I mean, I'm limiting the number of moves here. I'm pretty strict. This is with just 2.3 of the servers that are allowed to move. You get some Pareto curve that is, of course, worse than the one of the benchmark, but it gets closer as we increase the number of moves. With 9%, we are already getting pretty substantial improvements, around 80% to 100% if you look at this point, 100% in fault tolerance, and around 40% in bandwidth, with less than 10% of the servers that are moved. So, yeah, so part of this approach is actually deployed in production, and the way it works is that in every hour, let's say, for example, only a few swaps are allowed. A very small number of swaps are allowed. So just to conclude this part, so we showed the sort of the optimization, the placement of physical machines, or the assignment of physical machines to services. We showed the principled approach to dealing with both bandwidth and fault tolerance, which takes into account the communication patterns and can handle arbitrary fault domains. So this quadratic cost function didn't assume anything about the topology of the domains. The reductions I mentioned that we are getting, and certain interesting extensions is, I think it refers to one of the questions that was asked before. Optimizing bandwidth across multiple layers is interesting, and the dynamic case or the time dimension is very important. For example, one scenario that is interesting here is let's assume that we know in advance that there's going to be some maintenance in a large chunk of the data center. So we can actually plan ahead. We don't want to be surprised by, we know that there's going to be a fault at some point in time. So how can we plan better in view of this more planned outages in the data center? And of course, there is always room for improvements in the theoretical front, approximation algorithms, and I've discussed it with a few folks, theory folks, and there are some interesting problems that we didn't have time or wish to solve at this point. Yes?
It seems like you could also look at this in terms of, your assumption here is, or your constraint, I guess, is percentage of nodes moved, or percentage of server nodes moved, or threads moved, however you want to look at it. But one could imagine it more as from the point of view of being a rate of movement. So I allow a rate of movement. So I allow move every X number of minutes or seconds or whatever, right?
Right.
That's an interesting way to look at it, because that's probably, you figure that allows you to converge, and you limit the amount of moves. You're going to have a limited impact on the.
That's a great question, and I think it's a very correct observation. And what I mentioned that actually we do in production, we don't limit the number of moves. We're actually more concerned about the rate of moves. And these are very similar. I just use the number of moves to be able to write some concrete optimization problem. But as you move, as you introduce the time dimension, you need to, of course, work with rates. And that basically, the solution is almost the same. And these two sort of metrics are pretty similar in the optimization context, if you think about it. Any other questions about this part? Okay, so how are we doing in terms of time?
We have 20 minutes plus, 25 minutes.
Okay, good. So second part of my talk, and I'll also have 2 slides towards the end on some just a brief look at some other stuff that I'm doing. So this is second part is about speeding up distributed request response workflows, or if you wish, a simpler way to state this is basically improving the latencies that you see in Bing. Okay, when you type bing.com or you search for something, how can we improve the latencies? Okay, so it's a well-defined problem, but it turns out, you know, that it's not a trivial problem. It involves a lot of aspects, and I hope to convey some of them here to you guys. So I don't need, this is like more of a, you know, advertising in the sense of like convince you that it's an important problem, and then you see some quotes from what I assume these are important people. I didn't gather these quotes, so but basically they show that I mean, basically they state that there is an effect, a direct effect on business, on revenues or whatever if the latency goes up. Okay, and I don't know exactly how these guys obtain these concrete numbers, but of course it's a major requirement, a major concern that everybody is looking at. Reduce the latencies. It has a lot of business-related impact, consequences, of course. So the point is that when we started looking at this problem, we looked at the different services in Bing. So when I say different services here, it's a bit different than the services that I mentioned in the first part of the talk, which were like internal services. Here it's more like web services. So you want to think of each web services maybe consisting of the services that I discussed in the previous, in the first part of the talk. So here a service is a web service, could be the entire Bing.com could be a service, Maps, Bing Maps could be a service, shopping, etc. So these are web services. So if we look at the latency, something interesting comes up. So this shows, this graph on the right shows the ratio of the 99th percentile of the latency to the median latency. And you can actually see that 40% of the services have the property that the 99th percentile of their latency, okay, the worst one, if you wish, the fourth, in other words, the worst 1% of the latencies is more than 4 times the median. So there is a large variance in terms of latencies. And actually, what you want to attack is this tail. It turns out when we discuss things with the product teams, they mentioned that they're mostly concerned about about the tail. This is what sort of, if you get some queries that are really bad, this sort of has an immediate effect on the quality of service, there are other words of the quality of experience, or whatever you want to call it. So the question is why, and then you have to start looking at the system and think of what is the Bing.com or any similar web service. It's actually, and I'll have a picture in the next slide, it's actually a very huge distributed system consisting of thousands of machines and different components that do different, sub parts of the work itself. So we can think of a service, and we're going to use the term workload, which I'll show in the next slide, but basically you can think of many stages. Eventually you get the answer, but you get the answer with advertising, you get the answer with some other things, and maybe with some, things that are related to Facebook or whatever. So it's actually a pretty complicated distributed system. A lot of things happen in parallel, and eventually you get the answer. But basically you can think of physical machines. There are many physical machines that are involved in this process, located at different places in the data center. There is network congestion. There are transfers of information between the different stages, and so forth. And of course, the scale kicks in, and we get basically a complicated system, and there could be, and this sort of explains the effect. And in the paper, we actually have a more concrete study of what are the reasons for getting this high tail latency compared to the mean. So this beast here is an example of a workflow of a web service. Then you can see it's very complicated. So the edges here correspond to communications between the different stages. So a stage could be a speller, could be ads, and as I mentioned, there are dependencies. And one stage, for example, could be, so we could have up to 150 stages, degree of 40, so it's a huge graph. The path length is could be 10 or more. Okay, from the top to the bottom could be you can traverse through 10 different nodes, and each stage can be complicated on its own. Each stage could be something like this that I'm showing here. Each stage could correspond to different inner stages or inner stages of this particular stage. Here you have an example of partition aggregation. So think of it as a workflow, as a huge graph. Each component in the graph is ran on different physical resources, produces a result, and there could be some variance in its result, in the timing of the result, and the variances could add up actually, and you can get very bad performance eventually.
So Isha, is this an actual request?
So this is the actual DAG, direct acyclic graph, that handles the request. The request comes here from the top.
Right.
And
so what I meant was this is a real life example.
What?
Is this a real life example?
Yeah, this is a real life example.
So it's this messy, is it? Okay.
It's messy, yeah. I mean, I'm not an expert in distributed systems. There is some logic as to why things are designed this way. And I don't think we need to get into this question, but let's take it as given for the sake of this talk. But it's a good question whether, you know, there could be architectural improvements. That's a valid point, of course, but not in this talk. Any other questions about workflows? So I hope that I convinced you through this beast that it's fairly complicated. The resource allocation here is, we know the goal, but we started this and we didn't know exactly how to approach this. Okay. So, well, just one word about the related literature. So there has been work on latency reduction in the CCOM community, but the context was more on the network level techniques. You have a point-to-point communication, and for example, you want to make it aware of deadlines and so forth. But here the context is, if you think of the networking layers, we are looking at the application layer, and we are taking a more of like, instead of a point-to-point approach, we are looking at the end-to-end application latency, and we're trying to improve it. So what are the application level techniques that we are going to use? And the question is how you use them, because the techniques are out there and they're not rocket science on their own. I mean, they're pretty straightforward, and I'll just give you a few examples, what I mean by application level techniques. So the first technique is that you have a given stage, I, let's call the stage I, so it's a part of the workflow, and it has some latency distribution, and I could decide to basically reissue the request to this particular stage. Okay, the part of the input to this stage, I can basically ask this stage to process again, reissue, and let's assume that it's drawn from the outcome of the latency of the second copy is drawn from the same distribution. Then, if we decide that latency is that if I'm seeing a latency that is above of this particular stage, that is above the timeout, I'm basically reissuing the request, asking it to be processed again. Then I'm going to get a different distribution, of course, a less skewed distribution. Still, there will be some, of course, some elements will take more time, but I'm going to change the distribution. The other knob that we have is terminate the requests early. Basically, I'm deciding that, in particular, it's actually more complicated than that, but I'm deciding based on some considerations that I'm timing out the request at some point. Then, and I can live with some incompleteness of the results. Maybe I'll touch on this, although it won't be the emphasis here. Let's say if the results, for example, are 95% ready, but it doesn't matter. I set a timeout here, a simple timeout for the sake of this talk. And basically, I will also modify the distribution. I will, of course, have the peak around the timeout itself, right? And this is a consequence of setting a timeout on the distribution of the stage latency. There are other actions that I will talk about less, priorities, preemption, and this is the induced cost. So why do we care about, why do we need optimization here? Because all of these techniques come at a certain cost. I mean, there's no free lunch here, and for you guys, it's almost free dinner. So reissues come at the expense of extra resources. Okay, I need to reissue somewhere. I need to allocate machines for these reissues. Incompleteness on its own is bad. Okay, if I'm deciding to sort of terminate a certain stage while it's not complete, then of course the quality is worse, and maybe there is some budget, quote unquote, that I could live with in terms of incompleteness, but I can certainly not have each of the requests being incomplete. And maybe I can do it to a small percentage of the requests, and I'll be a bit more formal later on. So we know the techniques, but the question is how to set these parameters. For example, how to set these timeouts or these thresholds, or when do you duplicate, when you incomplete, and so forth. So what we were sort of surprised to see is that in the actual system, when we started working on this, is that actually, you know, these different stages could correspond, for example, to different teams. Different groups work on, you know, software engineering work on different stages of this workflow. And the timeout policy is local. Each team decides its own policy. Okay, and this is of course bad because by doing so, you don't take into account the end-to-end picture. For example, if there is a certain stage that is not on the critical path in terms of latency, then we basically don't need to worry about this stage, and we don't need to apply any techniques to that stage. So this work is about a more principled approach to how to set the parameters of the different stages. We call it Quicken, a fancy name, for a simple sort of goal. It's a framework to find the per stage parameters, with the goal of minimizing the end-to-end tail latency. Again, it's not very formal, because tail, you can think of the 95th percentile, 99th percentile. We actually want to take care of the tail to some extent, with constraints on costs. So cost here would be additional service, would be a total budget on the overall incompleteness quality that I'm willing to live with. So in a nutshell, the system Quicken is as follows. So we know the budget, for example, the allowed relevance loss or the extra resources. We know the workflow description, and an important part is that we have the path query logs. We can measure the execution times of previous queries. What Quicken wants to do is get all this as input and produce the configuration parameters or the scheduling policies for each of the stages. And the requests that are coming into the system this is what will be used for these requests, and we'll get responses, hopefully with substantial improvements on the tail latency. Okay. So just a bit about the challenges, and I'll be focusing for simplicity on a very specific knob here, let's say the reissues themselves. Okay, so here we see how the different stages react to the fraction of I'm basically reissuing the slowest request in the stage, and basically we see that what's the reduction in the 99th percentile. As a function of the reissue budget. So we can see that different stages react differently to the same budget. There is one stage that is very responsive, the latency drops immediately. There are some stages that basically are not very affected by this using reissues. And of course it has to do with the underlying distributions of the stages latencies. So the point here is that I'm trying to make here is that basically if you don't take this into account, let's say you want to assign the same reissue budget for all stages, you'll be wasting your resources because you're going to be assigning resources to stages that basically don't benefit much from this knob. So that's one challenge. The other challenge is that if we take into account the cost of using this knob, the cost is very different across different stages. If there is a stage that is basically a single machine, then of course I can do reissues. It's fairly cheap to do it because I only need to sort of use maybe another machine to do the reissues. On the other hand, if I have a very complicated stage that consists of different of many inner stages, then it gets more complicated. If it's partition aggregation state, then I need to use more resources for the same budget, for the same ratio of reissues. Okay, so the cost is very different here. And if you wish, each stage has its own a very different cost coefficient. Third thing is that the composition of end-to-end latency percentiles into individual components is hard. I don't know exactly what it means that if I'm reducing the latency of one stage, if I'm reducing the 95th percentile of the latency of a stage that it's somewhere in the workflow, it's not clear, a priori clear, excuse me, what's the effect on the end-to-end latency. In other words, these latency percentiles do not compose or do not add up. This is a simple, exercise in probability. For example, minimizing the 95th percentile in each stage doesn't mean that we minimize the 95th percentile of the end-to-end latency. So, I'll talk a bit about the principle of the design, and I'll show some results. I'll be fairly quick here. I'm seeing that I'm running a bit out of time, and I want to leave a few minutes for other topics. So this is the most important slide in terms of the end-to-end design. So so we have this workflow. Let's have a cartoon of, like, let's say it has 4 stages, and we have certain requirements from our design. First of all, we want it to be robust. We don't want to overfit or to care about a certain percentile. We want to care about all the percentiles. And here comes to the picture, we decided to focus our optimization on the variance, the end-to-end variance of the latency variance. Why variance? So basically, the motivations comes from something like Chebyshev inequality, whereas a deviation from the mean is proportional, no matter what deviation you use here, is proportional to the variance. So if you reduce the variance, you essentially or intuitively take care of all the percentiles at the same time. But we have, but we don't have a single stage, and we don't know what's the variance of the entire workflow. That's a very important, what's the latency variance of the entire workflow. So we want to have an end-to-end criterion that takes into account or that builds upon per stage measures. This is important in terms of simulating or in optimizing. You want to have per stage measures. So it's not clear if we have the variance of each stage, the latency variance, it's not clear what's the end-to-end variance, but what we do know is that the end-to-end variance is actually upper bounded by the sum of stage variances. This actually can be proven. How many theory guys there are out there in the room?
Enough.
Only you, so I won't go over this.
Yeah.
So you'll have to believe me, but basically, so the sum of variances is an upper bound on the variance of the end-to-end latency. Another point is that we have a very complicated optimization. We need to decide what to do with a given stage, how much reissue budget to assign to it. We want to have a tractable optimization procedure. So what we do here, we have a 2-layer optimization, and this is like maybe the most, bear with me, this is kind of the essence behind what we do. This is the optimization problem that we have. So basically, as I mentioned, we want to minimize the sum of variances of the different stages. The variance would change as a function of the amount of, here it's reissue, I'm using reissues, the reissue budget or the reissue percent that you're giving to this stage. This is similar to the response curves that I've shown before. So this is what you want to minimize, subject to a constraint on the budget. And as I mentioned, each stage has its own cost coefficient that corresponds to if a stage involves a lot of machines, the cost coefficient would be high. So what's nice here is that if you make a certain change in one of the stages, you don't need to start to simulate again the effect on the end-to-end latency or on the percentiles. You basically can just look at the change in the objective function. So this is what we mean by composability, which is very important. So one practical thing here is that instead of we actually don't know the functional form of the variances for sure, but what we do know, we gather data and we can measure, we can obtain what we call the response curves of the empirical variance response curves. This is actually the empirical variance. So actually, based on the intuition of Chebyshev, if you reduce, if you assign more reissues, then you can see that not only the latency drops or the 99th percentile drops, but the variance also drops. Okay, so there is a correlation between variance reduction and reducing the percentile latency. So just a couple of words. How much time do we have, more or less?
Let's say 10 minutes, 15 minutes. Stop.
Including questions? And
I had a question kind of related.
Yes. Sorry.
Maybe I missed it, but did you talk about why the expected value, like why the actual latency is not in optimization? Why you're working on?
Is not what? Sorry.
Well, so you're minimizing the variance, right? But what about the actual expected value at the delay?
So I guess the question is about the actual value of the delay. So
yeah.
The thing is, it's a very good question. The thing is that I'm more worried here about the tail latency. The tail is directly related to variance, and moreover, what actually makes this work nicely is that the value itself is also proportional to the variance. So if you wish, intuitively, the expectation is proportional to the variance. So otherwise, you wouldn't be getting the benefit. And you're right that in principle, if there is not a good correlation between the mean and the variance, then you can get all sort of weird things. But here, the case is also the mean is proportional. So if you have in other words, if you have a large variance of a certain path, it's more likely than this path is also a critical one in probability, but nothing is deterministic.
So I guess I just missed the part about the expected value being proportional to the variance.
Yeah, you didn't miss it because I didn't mention this. So you were right on. So that's a great question. Thanks. So just a few words about the simulations. So evaluation, we took the most used workflows at Bing, and we actually can see this graph shows that by 5% of budget, of reissue budget, meaning 5% more of extra machines, you can get to up to 30% reduction on the 99th percentile of latency. If we combine two techniques, we are allowing for a certain, so actually what I didn't say, but this exact formulation, the same formulation that we see here, you can think of it also in terms of quality loss. So you can, when you're able to return incomplete results, you can also formulate it in this way. Here's the sort of the percent or the ratio of incomplete results. You can formulate using the same optimization form. That's what's nice, that multiple knobs fall under the same umbrella of the same optimization umbrella. So we actually, in our experiments, we combine two techniques, and we show that the actual combination is better than each technique on its own, which is maybe intuitive, but was important to show. And with combination of the two techniques, you can get up to 75% reduction in the 99th percentile with 1% of reissue budget and a quality loss fixed at 0.1%. So that's pretty nice and pretty substantial results. Okay, so this is Quicken, and I had to be a bit quick here in presenting this, unfortunately. But sort of the takeaways are that we have complex workflows that lead to high tail latencies, and the techniques that we've seen that were used in an ad hoc manner in a pair stage without taking into account an end-to-end view of the entire workflow. And with Quicken, we reasoned about, we took an end-to-end approach, and we have like a layered optimization. So this thing here, I didn't emphasize, but here under the var Ri lays down basically, we abstract away the algorithm or the mechanism that we use per stage. So it could be simple, such as a reissue threshold, but it could be more complicated, and everything is abstracted away for the two-layer optimization. All we care about is the resource usage and the reduction in variance, but actually there could be a more complicated within stage algorithm.
Also, you're kind of taking a black box approach to each stage, right? You're just using the response curve.
Right, exactly. Okay, so yeah, so maybe I'll put the end slide first, and then I can discuss in a few minutes some another topic if you're interested. That sort of, I have just one slide on, but my point is that in terms of research, you know, especially when you're in a university and you have to write grants, and I guess Srinivas knows it quite well, you know, oftentimes you say, oh, my research is interdisciplinary. So, but I think that in the context of large data centers, a lot of elements come up, and this is just a few blocks of different disciplines that actually you need to know a bit about each, or know to ask the right people in order to solve certain problems. So there are some queuing problems, there are some scheduling algorithms, but also, of course, system knowledge, computer architecture, sometimes machine learning to reason about the data in a nice way. So this is why I like to be in this space. Srinivas knows me for quite a while. I have many interests, and sort of for me is there a right place to be right now, and I'm very excited about these opportunities of these interesting problems that arise. So yeah, so just very briefly, another topic that I'm working on. I call it paper performance. So it's around the economics part of pricing cloud services differently. And here's a simple example. So currently, if you want to use the cloud, you basically pay for, you buy 5 machines and you rent them for a certain number of hours, and this is what you pay. So in a line of work that with these co-authors, we thought, or we consider a different mechanism in which you want to pay for quality. So what you care about is not that you're getting 5 machines. What you care about is that, for example, in the batch context, you have a job that requires a certain amount of CPU cycles, CPU hours. And basically, you don't care exactly how you'll be allocated these resources as long as you get enough resources by a certain deadline. So here is a different protocol or a different mechanism, pricing mechanism. We'll have a job of size, so the user will specify the job size and the deadline. And again, this is a simplified setting. We actually have a more realistic, because there are certain considerations, parallelism considerations, and so forth. I won't get into this, but in a very basic setting, job of size D, deadline is T, and I'm willing to pay a certain amount of money, and now the cloud needs to decide how to schedule. Think of a Tetris game, how to place all the different jobs. Here you see a single jobs. How do you place all the jobs that each job meets its deadline and basically gets enough resources? And so there are 2 questions here. One is the scheduling, which on its own is very interesting, because these are all hard scheduling problems. The other is, of course, mechanism design. I want to sort of make the users tell me what their job is worth, or what the different deadlines are worth to them. For example, Srinivas could have a deadline For 4 p.m., what time is it over there? For 5 p.m. he's willing to pay $1,000, but for 6 p.m. he's willing to pay only $200. I want to extract this information from him, and those of you who are familiar with the algorithmic game theory concepts of incentive compatibility, actually these are not algorithmic game theory, these are more economic concepts. Incentive compatibility, you want to design a scheduling rule that is also incentive compatible, and this brings very interesting research questions. And beyond that, I'm hopeful that the pricing schemes would progress, at least in the way that all this cloud space is progressing. There's certainly, I believe, things to do in the way that resources are being sold and services are being offered. Okay, this is all I have to say. Thanks for listening, and I'll be happy to take questions if there's still time. Thanks.
Thank you.